Hello and welcome to ASMR Chemistry. We are going to go through a homework assignment together. And in fact, this is me creating the key for my class. And I decided we could do it together and you could see what it's like, how to sort through these kinds of problems, and see how I create my answer keys. Okay. So this particular key is for a homework that has to do with combustion reactions. So there's a few questions have to do with combustion and fuels, but then it also goes into a couple problems with thermodynamics, including heats of formation, otherwise known as enthalpy of formation, and looking at entropy and Gibbs energy as well. So you're going to get a good variety of problems here. Okay, so this is the answer key, so I'll name it as such. Okay. So this first question here, it has to do with combustion in general, and if you are specifically combusting hydrocarbons, okay, so carbon-based fuels. And so in other words, you're reacting them with oxygen. And when oxygen is in excess, you get carbon dioxide and water. But I remind my students here in this prelude that if there are lower levels of oxygen present, you actually get carbon monoxide as a product. Or if it's even lower, you'll actually just get pure carbon. So that's why sometimes you'll see the fumes coming out of an exhaust pipe in a car and black smoke comes out. That's actually carbon. It means there's a very inefficient motor that is not giving out carbon dioxide. Okay. So this first question is writing out the combustion of butane. So this is C4H10 reacting with oxygen. And this would be under normal conditions. In other words, oxygen is in excess. And we get that more common product, CO2, as well as water. So this is a little bit of a review as well, just balancing chemical equations. And I've taught this before in other videos, but I will just to let you know my process is I always balance them in order of carbons first, followed by hydrogens, and then oxygens last. That I have found to be the most efficient way to balance combustion reactions. And part of the reason is, you know that here you have 4 carbons, so you're going to end up with 4 here with this carbon-based emission. Okay, next I look at the hydrogens. That's going to be over in the water. So here it's H10, water is H2O, so I know that this will be 5 since it gets multiplied by 2. 5 times 2 gives us the 10. And then lastly, I can add up the oxygens that appear here as well as in the water, and however many I have on this side, that will be in the numerator of a fraction to balance out the oxygen, since it's O2. Each of these oxygen molecules has 2 oxygens, so here we have 5 oxygens on the product side, plus the 8 from the CO2. Okay, so we have 13 total oxygens. And because it's O2, we divide that by 2. Fractions are rare in balancing chemical equations, except in combustion reactions, because of the convenience of just putting in the value of the number of oxygens on the right side. Oops, sorry, I just wrote on that. And divide it by 2 since this is a diatomic. Okay, let's look at when the oxygen ratio is lower, such that carbon monoxide is formed, and we'll do the same thing. We'll balance these out. So now we have the same butane reacting with O2. still going to go with the 5 in front of the water to get our 10 hydrogens. But now the number with oxygen will be different. We have 5 plus 4 is 9. It's 9 here, too. Okay. So now if there's even less oxygen available, get different products once again. React with oxygen. Form now just carbon and H2O. So once again, there's 4 carbons on this side, put a 4 there. And there's 10 hydrogens, so I'll have 5 there. It's oxygens that are different. We have just 5 oxygens on that side. So 5 cells. Okay. The next question has to do, once again, with hydrocarbons. And it is acknowledging that there's a pattern for hydrocarbons, specifically alkanes, where there's a formula CnH, 2n plus 2, to get the overall formula for alkanes. So this question then is asking, what if you have heptane? Okay, 7 carbons. So we follow that formula. There's 7 carbons, and number of hydrogens, we'll double that, 14, and we'll add 2 to it. That makes 16. Okay. And then what is the formula of an alkane with a ridiculously large number of carbons? And this is just asked to essentially lock in that it's truly just a formula. We don't need to write out the whole structure or anything like that. So we have C171H, and I'm going to use my calculator. 171 times 2 equals 342. And then we'll add 2 to that. Make it 344. Okay. All right. And the last question. Let's draw out some isomers. Okay. So here's a compound that has an oxygen in it, as well as carbon and hydrogen. So let's see what kinds of formulas we could create with this. All right, line angle drawings. So here are 4 carbons, 1, 2, 3, 4. And then I'm going to try bonding an oxygen OH group to this. Okay, let's see how this works. Does this give us this formula? And we can test that. Okay, so with line angle drawings, hydrogens are implied. They're not shown explicitly. But where we have this carbon here is bonded to 2 others, that means we're going to have 2 hydrogens there. I'm going to put 2 little dots there. Oh my gosh, they look like lone pairs. I do not mean to do that. I'm just counting. So hydrogen, 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 hydrogen. This one's at the end, so in order for the carbon to have its octet, we need those 3 hydrogens. All right, so do we have 10 hydrogens? 2, 4, 6, 8, 9, 10. Yes, we do. Okay. So I'm going to put a little note here. Dots represent hydrogen atoms. Just essentially to count them up, right? Okay. Now, what about if we made an isomer, a structural isomer of this? Okay. So we could have, let's keep this OH group the same, but there's a carbon, and how about some branching? Okay, so if we had branching like this, 1, 2, 3, 4 carbons, and then we can count out the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. Put dots. Okay. 3, 6, 8, 9, and there there's another hydrogen right in there. Okay, there's the 10th one. All right, I bet we can branch this even more. Let's try this. See how this works. OH. Okay. 1, 2, 3, 4. All right, there's 4 carbons. 1, 2, 3, 1, 2, 3, 1, 2, 3. All right, so 3, 6, 9, 10. All right, awesome. Okay, how about we could try putting oxygen in the middle. Okay. So there's a carbon, there's a carbon, there's a carbon, there's a carbon. All right, so here we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. There's the 1 oxygen. And that works out too. Okay, so there are 4 structural isomers. I'll spell these arrows. It really is kind of bugging me that these look like lone pairs, but because they're like clusters of 3 and there's 1, things like that, hopefully that's clear. Okay. So this question was in here because we learned about line angle drawings since we were talking about combustion of fuels, and there's so many carbon-based fuels. So learning a little bit about line angle drawings for alkanes is something we did, even though it was not an organic chemistry class. This is in a general chemistry. Okay. So here we get into some thermodynamics, and specifically we're looking at enthalpy for this reaction here. Okay, so this is kind of a combustion reaction, but now specifically metabolism. So this is metabolism of glucose. Here's our glucose reacting with oxygen and giving CO2 and water. Again, very much like and does fall into the category of combustion reactions. This is exothermic as expected. We have a negative sign for the enthalpy. Okay, we're always going to see exothermic for combustion of hydrocarbons, all right? And now let's get to the question, all right? The mass of glucose in a 1 liter bottle of Canada Dry ginger ale is 46.5 grams. I looked this up. Oh my gosh, isn't that just kind of crazy? Whew. Okay, anyway, calculate the enthalpy change for the metabolism of glucose if someone were to drink the entire bottle. Okay, so in other words, drinking the entire bottle means consuming 46.5 grams of glucose. The molar mass of glucose is, and we are given it in grams per mole. Okay. Now, as a side note, you might be thinking, hey, what about the sucrose? Sucrose is a sugar, is more the common kind of sugar that we buy at the store when we're going to bake, etc. There are many different types of sugar, and glucose is just one of them. But we are just looking at glucose in this problem, and it was indeed glucose that I looked up, that there is this amount of it in the Canada Dry ginger ale. There's also sucrose, but that would be a different problem. Okay, I'm just going to focus on this equation here, the metabolism of glucose. Okay, so we're given that the person has consumed 46.5 grams. Here's the molar mass. We're going to convert to moles. When in doubt, calculate moles. That is my mantra. When in doubt, calculate moles. Okay. So this is 46.5 grams divided by 180.16 grams. All right, and so we get 0.2581. 2581. moles of glucose. Now, you might be saying, hey, professor, what's going on? You just gave 4 sig figs, but the problem only gave you 3. I usually carry one along for the ride until we get to the very end of the problem, and that helps to prevent something called a round-off error, okay? It would be okay if you did not do that, at least in my class. I wouldn't take up points for that, but that is something I do. Okay, so now we're going to calculate how much, what is the enthalpy change for this particular amount. We were given that the enthalpy change per mole is this, minus 28.16 kilojoules. Okay, and this is for 1 mole. So I'm going to write it this way so that we can see how this is going to cancel out moles from here. 25.81 mole. Okay. So I still have this value here. Multiply by 28.106 negative. And we get minus 727. Minus 727 kilojoules. Okay, so now I have gone back to my sig figs rules, and we get 3 ultimately because we had 3 in the beginning, and there would be 727 kilojoules released, or in other words, a change in enthalpy of minus 727 kilojoules. Wow, that's a lot of sugar. I'm trying to wrap my head around that, like putting that into your body, but hey, that is what you get when you drink soda, and guess what? Our brains need glucose to function. So, all right, now we're going to answer some more qualitative questions. They are hearkening back to calculation we just did and this information that was given about the enthalpy for this reaction, but this is to help us understand this idea about forward reactions and the exact reverse reaction, okay? So this question here is talking about photosynthesis. Photosynthesis is the exact reverse of the chemical reactions shown above, where plants use CO2 and water to create glucose. Okay, so now it's asking, write the chemical reaction corresponding to photosynthesis. All right, so what we're going to do, it's the reverse reaction, so we are going to write this out in the opposite direction. We'll have the same number of carbon dioxide, water, oxygen, and glucose. We're just reversing the products and reactants. Okay, so we've got 6CO2 plus 6H2O. That is forming 6H12O6 plus 6O2. All right. Now, as a side note, we're going to be acknowledging this later, but this CO2 is gas phase. Water can be liquid or gas depending on if it's water vapor or not. We have solid glucose, and then O2 is a gas. Okay, so based on the enthalpy value given in problem 5 for combustion of glucose, okay, this was given, write the value of enthalpy for the photosynthesis reaction. I give a hint here, no calculation should be necessary, because what we are saying when we reverse a reaction is that any of the thermodynamic parameters will simply be reversed, the opposite sign. Okay, and in this case, this is enthalpy, and it will now be positive instead of negative, 2816. kilojoules per mole. Okay. Now it's based on the calculation that was done in problem 5. Oh, that was the previous one. I think that should have been 4. Let me fix that. What is the value of enthalpy for the creation of 46.5 grams of glucose via photosynthesis? All right. So now we're saying this is the exact opposite, reverse reaction for the same amount. So that means the amount of energy absorbed would be the same, but opposite sign. 727 plus 727 kilojoules. Okay. Now we're going to think a little bit conceptually. Okay. The sign of entropy. Okay. So we're going to think about a number of moles of gas molecules and liquid molecules. Let's put gas, liquid. Here, this is solid, right? And this is gas. All right. So, if we're looking at, based on the chemical equation for metabolism of glucose, given in, so notice how when I'm making the key, I will find errors, and so I fix them, and then I correct them on the actual assignment. So, okay. All right, so we're looking at metabolism of glucose. So let's look back up here. All right, here's our glucose, solid. This is our oxygen gas. Here is CO2 gas. And we'll call water liquid, so it's at room temperature. All right, so we have one molecule here that's fairly complex, and we have 6 gas molecules. And then this is forming 6 gas molecules and 6 liquid molecules that have a lot more movement. Over here, we have much more possibility of the molecules moving around. So in terms of entropy changing, we're going from more structured, confined molecule and some gas particles that are then finding more locations that are available to them, especially by virtue of, instead of having one solid molecule, we now have these 6 liquid molecules. The number of gas particles has stayed the same. The impact of entropy is biggest when you have a change in number of gas particles, but we are still seeing a bit of a change here from the 1 molecule going to the 6 molecules. 1 molecule solid, very confined. 6 molecules liquid, those can move around. Okay, so we would expect entropy change to be positive. Okay, there is an increase in the energy dispersion in the system. Is a reaction spontaneous or non-spontaneous? Well, for all combustion reactions, they are spontaneous. And we especially see this because we have negative value of enthalpy and positive value of entropy. When this is true, these types of reactions are spontaneous at all temperatures. Okay, and then photosynthesis, this is the opposite reaction. Therefore, it is non-spontaneous, meaning it requires an input of energy to happen, which it gets from sunlight. Okay, let's continue making this answer key. Okay, so this is, we're going to be calculating, these are heats of formation, and we're going to be calculating the heat of reaction from heats of formation. We do this by summing up all heats of formation, the products. We subtract the sum of all the heats of formation, reactants. Okay. Oh my gosh, I need to bring this down. Okay. So here's the chemical reaction. CH4, Cl2, CCl4, HCl. It's balanced. And we have the heats of formation given in kilojoules per mole for each one of these molecules. Notice how Cl2 is 0. This is because this is elemental chlorine as it exists under standard conditions. Heats of formation are 0 for elements. Okay. Alrighty, so let's look at all of these. Heats of formation of the products. We have a minus 139.3. This is kilojoules per mole. We're adding it up with heat of formation of HCl, but notice there is a 4 there. So we will be adding this to 4 times minus 92.3 kilojoules per mole. Okay, then we're going to be subtracting heat of formation of the reactants, okay, which we have minus 74.8 kilojoules per mole. And we would be adding this, why don't I bracket this off so we can see how this works. Adding this to 4 times, because we have a 4 there, but it's 4 times 0. Okay. So let us now add these up. We've got, I'm going to start with this one. I want to multiply this out. 4 times 92.3. Okay. I'm going to add this to minus 139.9. 39.3. I feel like I said 9, but 139.3. Make sure I make that negative. Okay. And now I'm going to subtract a negative number, which is the same as adding a number. So I'll add 74.8. That's 74.8 equals. Okay. We have an exothermic reaction here. Minus 430. Let me just double check in terms of sig figs. It looks like we get to keep the 1 past the decimal point, so 7 kilojoules per mole. Okay. Awesome. Alrighty. Now let's do a calculation that is delta G. We've got Gibbs Energy, and we have enthalpy that's given, and we have entropy that's given. So notice that the units of enthalpy are kilojoules per mole. Those that are standardly given for entropy are joules per mole Kelvin. So one of the first things that I commonly do is I convert this to kilojoules per mole Kelvin so that all the units are working out. Okay. So 0.0367 kilojoules per mole Kelvin. All right. So it asks that we calculate the Gibbs energy. So here is our equation for that. D delta this. Now, notice that it didn't give you a temperature, but it is indicating that it's standard conditions with these superscript naughts or zeros. Okay, that means standard conditions, which means we're looking at 298 298 Kelvin. Okay. Standard conditions 298 Kelvin, 1 atmosphere pressure, if it's a solution, 1 molar, etc. Okay, so now we can calculate. Put in our values. This is endothermic reaction, 64.4 kilojoules per mole. Then we will subtract 298 times, and here we converted this to kilojoules per mole Kelvin. 367 kilojoules per mole Kelvin. Okay, so that means that our Kelvin will cancel out with the Kelvin, and we'll get our final answer in kilojoules per mole. Alright, so I usually multiply these out first. So this is 298 times 0367. 367 equals, okay, 10.9. Okay, so I'm just sort of looking ahead, and I know that I'll be taking the value of enthalpy, and 64.4. So I know the best I'll be able to do is 1 past the decimal point. So that's why I'm looking at this and going, okay, 10.9. Okay, make that negative and add in the 64.4. Okay, 53.5. All right, that is positive. That is a positive value. No, it was not. Okay, so look at this question here. Based on your calculation, is this reaction spontaneous at 25 degrees? Okay, so 25 degrees is 298 Kelvin. And we just calculated that the Gibbs energy is a positive value. That means it is non-spontaneous. So, no. And I like to give a little bit of an explanation, even though I didn't ask for it here. Delta G is a positive value at this temperature. All right, now it's asking within what range of temperatures is this reaction non-spontaneous? Okay, so notice for this particular reaction, we have a positive enthalpy and a positive entropy. Okay, so that means you can actually change the temperature and make it spontaneous at certain temperatures. So here is the question. Within what range? All right. And the way you do this kind of problem is you first acknowledge, okay, what's our relationship between Gibbs energy, enthalpy, temperature, entropy. And now we are going to find the cutoff, okay, the cutoff between it being spontaneous and non-spontaneous. Spontaneous would mean that delta G is negative. Non-spontaneous, like we just saw, is when delta G is positive. So what is the cutoff point between a positive number and a negative number? It is 0. So we are going to find that cutoff point So we're going to set delta G equal to 0. All right, this is how you solve this kind of problem. Now we are going to solve for temperature. So that means we are going to add T delta S to both sides and then divide by delta S. And it is delta H divided by delta S. Okay. The units are going to work out because enthalpy is in kilojoules per mole and entropy is in kilojoules per mole Kelvin. So that Kelvin that's brought in here, denominator of a denominator, moves to the numerator and we will get the temperature in Kelvin. That's the cutoff point. Okay, so let's continue here. Temperature equals, let's put in the value of enthalpy, which is plus 64.4 kilojoules per mole. And we'll keep the entropy in kilojoules per mole K again, and that is plus 30. Oh, I want to make sure I get it right. 0.00. That is a 0. 367 kilojoules per mole Kelvin. All right. We're now going to divide these. 64.4 divided by 0.0367 equals. Okay, so we have 1755. I guess we only get 3 sig figs though, so 1750 Kelvin. 1750 Kelvin. Now to really show that there are 3 sig figs, we can also write this as 1.75 times 10 to the third Kelvin. Okay. Now, the question is, this is the cutoff point. It's a pretty high temperature. Okay. And is it at temperatures that are greater than this or temperatures that are less than this when it is non-spontaneous? Okay, non-spontaneous. Notice that at a temperature lower than this, we got a non-spontaneous answer. The delta G was positive 53.5 kilojoules per mole. So at a temperature lower than this, it was non-spontaneous, and then this is the cutoff. So therefore, we can conclude temperatures less than 1750 Kelvin, this reaction is non-spontaneous. Okay. And just as additional commentary, side note, at temperatures higher than 1750 Kelvin, the reaction becomes spontaneous. Delta G is negative if you get the temperature high enough. Okay? Because of this influence of temperature on Gibbs energy, if you make this high enough, then now this T delta S value is positive enough that it overrides the fact that it is an endothermic reaction and it makes delta G negative. But you got to get pretty hot to make that happen in this case. Okay, that is the homework assignment. That's the last question on it. So thank you for accompanying me as I worked through creating the answer key for this particular problem set. And hopefully some of these problems were helpful for you, seeing some of these types of questions. And I like how there's variety in there, so you can see different types of problems all together, all in one video. So thank you very much for joining me. And as always, I so much appreciate the comments that I get. The requests are great, so keep those coming. And let me know if there's anything else I can do to help you, support you on your chemistry journey. So glad to be here with you. So take care, and I will see you in the next video.